Hello everyone. The topic I was discussing earlier, it was in the unit operations in food processing, and the topic is about filtration. In this, we have discussed about what is filtration, what is the process involved in filtration, and how it is removed, and what is a filtrate and a filter cake, and what are the important factors that influence the rate of filtration, and the applications involved in filtration, and what is the filter cake filter clarifying and the cross flow filter, and the requirements, filter rates, etc. And in the next session we are going to see about what is the filtration equation for constant rate filtration. In early stages of filtration, filter medium resistance is relatively large when compared to the cake resistance. So the resistance offered to flow is constant and the filter proceeds more or less at constant rate. Delta P is equal to V by AT into mu or into W by W into V by A plus L. Then filtration is a constant pressure filtration, and the design considerations. The surface area of the filter time filtration, feed rate, initial and final solid content, filter medium resistance, filter cake resistance, pressure drop, thickness, and viscosity. These are the design considerations required for the filtration. And here's the equation. And the membranous filtration medium. Membrane, it can be defined as the barrier that separates two phases as a selectively wall to the mass transfer, make the separation of the components in a mixture possible. Driving forces. A driving force, it can make the mass transfer through the membrane possible. Usually, the driving force can be pressure difference delta P, a concentration difference delta C, and an electric potential difference delta E. Membranes can be classified according to the driving forces. Delta P is microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and piezo-dialysis. Delta C is given as per evaporation, gas separation, vapor permeation, dialysis, and diffusion dialysis. And delta T, change in temperature, it is thermoosmosis and membrane distillation. And delta E is electrodialysis, electroosmosis, and membrane electrolytes. These are the classification of the separation process according to the particles retained. First is microfiltration. In this, particles are suspended. In ultrafiltration, macromolecules are retained. In nanofiltration, sugars are retained, and in reverse osmosis, salts are retained. For microfiltration, the pore size of the particle is 0.1 to 10 micrometer, and the pressure difference is about 0.5 to 2 bar. For ultrafiltration, the microparticles pore size is about 1 to 100 nanometer, and the pressure difference is about 1 to 10 bar. And for nanofiltration, it is 0.5 to 5 nanometer molecules, and the pressure difference is about 10 to 70 bar. And for finally, in reverse osmosis, it is the pore size is more than 1 nanometer molecules. However, the pressure difference is 10 to 100 bars. These are the various sizes of the materials for various processes and driving force. Microfiltration. It is used to remove particles larger than 0.2 micrometer. Microorganisms cannot pass through them. It is operated at low pressure difference. It may or may not be asymmetric. It is used to remove bacteria and other spoilage microorganisms. Ultrafiltration. It is used to separate macromolecules and small microparticles from solvents, ions, and small molecules. It has smaller poles than microfiltration membranes. The driving force is 2 to 10 bars and to 25 to 30 bars. It is used to separate species with pore sizes, that is 10 to 1000 Armstrong, which is 103 to 0.1 microns. To separate a solution, desirable and undesirable mixture of components has to be present. It has small pore size than microfiltration membranes. The driving force and the pressure difference are all given. The flux rate to an ultrafiltration membrane can be obtained as N is equal to Ka delta P, where delta P is the pressure difference across the membrane, and K is the membrane permeability constant, and A is the membrane surface area. And here's a problem which is regarding this previous sum. And here are the wide range of applications of ultrafiltrations. Oil emulsion waste treatment, treatment of whey in dairy industries, concentration of biological macromolecules, electrocoat paint recovery, concentration of heat sensitive proteins, ultrafiltration of milk, bioprocessing, protein harvesting, and refining of oils. For nanoparticles, the pore size is lesser than the ultrafiltration. It operates at low pressures, that is 10 to 30 bar. It can be operated higher recoveries, conserving total water usage due to a low concentrated steam flow rate. Not effective on small molecular weight organics like methanol. Typical applications: desalination of food, dairy, and beverage products or byproducts, partial desalination of whey, UV permeate, or retentate as required, desalination of dyes and optical brightness, purification of spent cleaning place chemicals, color reduction and manipulation of food products, concentration of food, dairy, and beverage products or byproducts, fermentation, byproduct, and concentration, and reverse osmosis. It has materials larger than 1 micron and it operates at 35 to 100 bar pressure. It eliminates and dissolves solids, bacteria, viruses, and germs. Only water is allowed to pass through the very big pressure. And this is the equation and the formula. Thank you. And this is the extensive applications like pharmaceutical grade water. It is used as potable water for sea or brackish water. It gives municipal and industrial waste treatment. It produces processed water for boilers, etc. Thank you.